Hi, this is Brock Riddle, and this is a presentation on random number generation. Now, what is the importance of random numbers? You see, in early crypto systems, we had very few key variations. In fact, one of our earliest common ciphers was the Caesar cipher, which had only an effective key size of 25. Now, this was very easy to brute force attack because that meant that plain text could only be encrypted 25 different ways. Now, as we moved on to more sophisticated methods of encrypting our messages, we were still seeing that frequency attacks were very common. This was because they were still being encrypted based on languages and alphabets. And due to languages having patterns, it meant they were more vulnerable to attack, such as frequency attacks. Now, the solution to this was random number generation, as random numbers and its generation can expand the total possible keys we have for our crypto systems, as well as have less discernible patterns between keys. This helps us to not only make all of our encryptions more secure initially, but also make it more secure that if an attacker gains access to one key, they cannot use that to effectively calculate other keys as well. Now, there are two types of random number generation. We have true random number generation, which generates numbers based on real-world events. And this can be anywhere from rolling a dice to clicking a key on a keyboard. And then we also have pseudo-random number generation, which computationally generates random numbers based on an algorithm. Now, it's worth noting that perceived is in quotations because this algorithm cannot give you any actual truly random numbers. Therefore, this is only a pseudo-random number because the large numbers are only perceived as being random. Now, taking a deeper look at true random number generation, we see that this generation is based on physical phenomena, which are events occurring in the real world and often do not hold discernible patterns. And this can be anywhere from weather to radioactive decay. Now, it's worth noting that there are some who argue that with enough given information and intelligence and resources, it can be predicted on what weather will be like in a specific location. However, at the same time, the resources needed and information and cost of predicting such weather would often be far too great for it to be viable for attackers, in which is still regarded under a true random number generation. Now, some more examples of true random number generation include mouse movement, keyboard typing, atmospheric noise, which is worth pointing out that it does not only include storms or weather-related noises, but it can also be something as simple as a car running or a fan blowing in the background. All these ideas are atmospheric noise as they contribute to a noise that could be picked up as an electrical signal. Now, we also have radioactive decay and rolling a die. Now, rolling a die is actually a great example of true random number generation because while it can only generate 6 possible different random numbers, the information that's needed in order to predict or create a pattern on what the number next generated will be is far too great and would take far too many resources for it to be worth calculating. For example, for rolling a dice, you'd probably need something similar to the velocity the dice is thrown, the friction of the surface it's thrown at, and the air resistance of the die. Now, all of this is really not worth it compared to trying to find which of the one of 6 numbers it generates is. Now, looking at the first example we listed for true random number generation is mouse movement. Now, the overall idea of mouse movement is that we want to collect the position of our mouse on the screen as an X and Y position. And what we'll do from there is we'll multiply those two positions to gather our true random number. And then really we can stop there if we wanted to. But what we can do is we can actually pair it to go even further and set it as the seed for a pseudo-random number algorithm to generate yet another random number and go a bit further in our random number generations. So we can even see that here in the code to our left is that we import two libraries. We import the PyAuto GUI and the random library. The PyAuto GUI library basically just helps us to keep track of the mouse and where it's at on our screen. The random library, as I'm sure we all well know, is very effective at generating random numbers through pseudo-random algorithms. Now, what we do in this code here is that we go ahead and define that function of RNG mouse, which we'll just call to basically get that random number generation going. And what we'll do first in the function is we'll set the position by calling the position function within PyAuto GUI. And that'll basically return us the X and Y value of our mouse and where it's at on our screen. And we can see that down here is that we set the variable SD equal to the X position, which is position 0, and the Y position, which is position 1. And we multiply those to get our true random number. And we can actually see that in this example output down here is that in this case, the mouse was at spot 124, 717. And so what we did was we multiplied the X value of 124 times the Y value of 717. And that returned us the true random number value of 88,908. Now really, if we wanted to, we could stop there and say that's a good true random number to use, and we can, kind of end it there. However, what I wanted to point out is that we can actually take this one step further and use that for a seed for a pseudo random number algorithm, which we'll talk about a little bit more later. But I just want to go ahead and show it right now. So in this case, yeah, that's what we do is we set the seed equal to the X position times the Y position using the rseed function right there, which will set the seed for the random library as the 88,908 in this case. And then we go ahead and call the r.random, which we'll talk about that function later and how that works a little bit as well, which basically it uses that seed of 88,000 to generate a new random number, which we see as 0.66022 and so on and so forth. And so yeah, that's just a cool function of the mouse movement and how we can even use something as simple as that to generate a random number. Alright, so the second example we have here is atmospheric noises. So yeah, noises can be picked up as electric signals. Really, any kind of noise can be picked up. But I wanted to point out the quick note that thunderstorms really do work as a great source of random number generation. Because really, when you're looking for true random number generation through atmospheric noise, you want to pick up sources that will have a greater range of noises. Because really, the smaller the range of noises that's possible, the smaller the possible number of numbers you're going to generate. So that kind of follows that if you have something like a storm that can go either really quiet or really loud, you also have a now range of a much larger source of random numbers to go from. And so that kind of helps you to get more diversity in your numbers that you're getting. So I just kind of want to point that out. Also, it also adds a sense of unpredictability to the numbers you're generating, because if you're to say you do something like an office space as your atmospheric noise, and say there's something like a fan that's on a swivel in that office that you're picking up on, you would see that as the fan kind of swiveled around and as it got closer and pointed more towards the source of whatever's picking up that noise, it would be louder, and as it moved away it'd get quieter. And so you'd kind of see that as you generate more numbers using that you'd see the pattern of numbers of when it's quieter from the fan and when it's louder from the fan. And so an attacker could see the structure of the numbers and how it's being computed and find a pattern in that, which would decrease the security and kind of defeat the purpose of true random number generation. So really, storms are just a great example of that, because you can't really predict when lightning's going to strike or when you're going to have thunder. So it kind of does help break those patterns and makes it hard to predict or calculate what the number generation is. It also just gives you a great range of decibels to work with. So yeah, just want to point that out of what a good source is. And even the website random.org, they actually use this to generate their random numbers. They have many different radios throughout Europe that they use to pick up on atmospheric weather noises to get those kinds of good random numbers generated. And they even have a great article and paper talking about atmospheric noises and converting that to random numbers. They go very in depth on that, and it's just a great website to look at. And so after we pick up those noises as electrical signals, we take these signals and convert them to binary numbers. We use this using a analog to digital converter, or also just called a ADC. And we'll actually talk about this a bit more later, about how a ADC works. And it's a pretty cool little tool that you can use. I believe they actually have them for about $15, $20 on Walmart, to be able to just play around with the Arduino and Raspberry Pi. They also have some tools you can work with to try to test those out. And then after we convert those to binary, we can use that binary output to either use as the key and just take that as our true random number generation, or we can use that number as a seed for a pseudo-random number crypto system. And so really it just depends on whatever the need of your random number is, of whatever you choose to do with it. because obviously a true random number, you can use that as a key if you like, or you can take that one step like we looked at, like the mouse clicking, and use that for a pseudo random number algorithm. It's really just comes down to whatever your need is there. All right, like I was discussing earlier, we got the analog to digital converter, which is we've already picked up that noise as a electrical signal, and now we're trying to convert that into a binary output. So we see here that we've got two initial variables in this graph that we're looking at. Yeah, so we got these two initial variables. The first variable I want to talk about is the Vn, which is just the noise that that I was talking about earlier that we got as an input as an electrical signal. That's just going to come in the form of volts, and we'll just call that the Vn. And then we also have Vref, which is a predetermined voltage that we're going to be comparing the input voltage to, kind of comparing that against, just to kind of get an idea of what the size of the input voltage is. And so that's kind of what the entire purpose of this graph is to compare the input voltage and just kind of get an idea of how big it is to get that binary output. And so looking at this graph can be a little overwhelming, but just looking at it initially, we kind of see that as the input goes along, it gets compared against these values by the reference. And so what happens is as it goes through and it tests, for each comparison, the reference will actually go through a resistor right before that. So we see in this case that the reference starts at 4 volts. However, after the first resistor, it goes down to 3 volts and it compares it against the input. Now what will happen is that the input voltage must be greater than the reference. If not, it does not pass the test. It's marked as false and it continues down until it does pass true. If it doesn't ever pass true, it's going to always be marked as false. And so we see through here that Vn, we go through, we test. If it doesn't go through, we go down, we test against 2 volts. If it's not greater than 2, we go down again, we test at 1 volt. And then if it doesn't pass 1 volt, then we're just kind of done. We found out that it's not greater than any of them. And so looking at this graph down here, we kind of see the results of that. If the input voltage was 0 to 1, it would never be greater than any of these reference voltages that we see. So we see that all the comparisons, which are all the D values, are marked as 0. And in result, the binary output would be 0. Now, on the flip side, if, say, the input voltage were to be anywhere from 3 to 4 volts, we see that it'd pass the first test. So it'd say, okay, the voltage is, say, 3.5 volts. That's greater than 3 volts. So we'll mark the first comparison, which is D3, as true. And the funny thing about the ADC is that each of the comparisons have a value. So, for example, the very first comparison is going to be more valuable than the rest of the comparisons. So basically, they're kind of ordered as the initial comparisons are always going to be more valuable than the later ones. So basically, once you pass a comparison as true, it doesn't test for any of the rest, because it's kind of basically just saying, hey, I know it's this big, I know I don't need to test the rest of these because you're just going to pass the rest of these tests anyways. And so that's kind of what we see here in the X's, is that it passes the first test, so all the rest are marked as X because it automatically knows those are going to be bigger. And so the way it generates the binary output from this is that the comparison here is D3, which we see as the first one. And so D3, 3 in binary is 1, 1, and you can't quite see it here, but that's kind of what the output here is 1, 1, so that's just binary for 3. And we see in another one, if the input were 2 to 3 volts, it wouldn't pass the first comparison, but it would pass the second one. And from there, it would kind of say, okay, I don't need to test the rest, we're done. So it just passes true for the comparison of D2. And the binary for D2 is 1, 0, which, like you can't see it here just now, but that's what the output would be for that, is 1, 0. And so we see here that the binary output for this graph is always going to be a 2-bit output. So we kind of see here that this is kind of the equation that you kind of use to figure out what kind of ADC you want to build or set up to capture sound and get output for it. It kind of depends on how many bits you want. So we can calculate that by the function 2 to the x equals r. In this case, x is the desired amount of bits of output you want, and r is the amount of resistors you're going to need. So in this case, say we have 2 bits of output that we're desiring. That'd be 2 to the second power, which equals 4. And we see here that we do have 4 resistors in this graph. And as well, the same thing kind of works with comparisons, except for each comparison, it's always going to go through a resistor before it gets to that comparison, if that makes sense. So in this case, we see that each time we see a comparison, the reference has gone through a resistor before that. That's because it's constantly changing the size of the reference voltage, so that it's continuously changing the size of the voltage so that we continuously test the input against a new voltage that's continuously getting smaller and smaller so that we can find that range of just how big this input voltage is. Because it really wouldn't make sense to compare the input voltage against the same value twice in a row. It wouldn't do us any good in that case because it would get the same result. And so we see that for each comparison, it's going to have a resistor right before it. So really, you can also kind of get an idea of how many comparisons you need to do based on how many bits you want as well. The equation is just a little bit different. It's 2 to the x minus 1 is the amount of comparisons you want to do. So in this example, once again, if we want 2-bit output, that would just be 2 to the second power, which is 4, minus 1 is 3. So we see here that we have 3 comparisons to reach a 2-bit output. On the flip side, if you wanted a 3-bit output, that'd just be 2 to the third, which is 8 minus 1, which would be just 7 comparisons and 8 resistors we'd need in that ADC for a 3-bit output. And so that's just kind of how that goes. And yeah, as long as it passes true on any of these comparisons, like I said earlier, all the rest will be passed as just automatically dropped because it knows it'll pass it anyways. And that's just kind of how the ADC works. And honestly, it's a pretty cool system. And I'm pretty sure Arduino and Raspberry Pi, they have some DIY kits that you can make your own ADC with for about $15, $20 if you just want to play around with it. Alrighty, so the next method for generating random numbers is the pseudo-random number generation, which we've been kind of talking about a few times, but we're really going to dive a bit deeper on that now. So yeah, this we just computationally create random numbers using an algorithm, so it's very much not truly random. It's all computationally, mathematically generated. And so we see that even though it is generated, many modern algorithms have the computing power now to very much appear random. It produces amazing numbers to where we're pretty convinced it's random, even though it's very much computationally created. And that's where we get the name pseudo-random, is because even though it appears very random, it's still very much calculated. And so yeah, that's kind of where we get that name from. And we often see that like it's all the pseudo algorithms are based on seeds, and that's ultimately what goes into producing a random number through these algorithms is based on seeds. And you'll see that if you use the same seed for the same algorithm over and over, you're going to keep getting the exact same random number. And that's kind of what opens up these vulnerabilities within pseudo-random number algorithms, is that if the attacker eventually guesses the seed and gets the seed right of how you've been generating your numbers, they can ultimately get access to the key, which helps them to break more ciphers and get access to information they shouldn't have access to. Alrighty, so yeah, we're looking more into pseudo-random number generation, and we're just kind of looking over the outline of how a lot of the algorithms compute the pseudo-random number value. And so yeah, we'll see that ultimately it starts with the seed. Almost every algorithm will start with a seed. Really, you can't go very far without it. That's ultimately where it'll start, is that, and it's one of the most crucial parts of the algorithm is the seed. So you always want to keep an idea of how you're getting your seed and how you're storing it and how you compute it, And so we'll see that it starts with the seed, and we take the seed and we put into this initialization function. And that's kind of just a one-way function that we'll use because really you don't want your attacker to be able to reverse calculate or do anything to basically find out how you calculate your seed or get access to that. So it's just kind of a one-way that will get you into your state. And now the state is a very important part of the algorithm as well, because that's kind of where you'll be keeping the current random number that you've got, and that's what you'll be using to calculate the next random number. And so you want to keep track of your state, because if you don't know what random value you're at now, you won't be able to generate the next one. And so that's kind of what the algorithm does. It takes the current random number and it uses that to use the transformation function to generate the next random number. And you'll kind of keep doing that cycle over and over. You'll take one state, you'll generate a new random number with that state to get a new state, and you'll keep doing that many times over until eventually it does it however many times you like. And then you'll use an output function to basically do another one-way function just to make it more random, make the patterns harder to detect, make it more difficult for the attacker to understand why it's not random, because like I said earlier, there's no such thing as a truly random pseudo random number generation. And so even though it's not truly random, we don't want the attacker to think that. We want them to have a hard time understanding the pattern between these random numbers we're generating. And so that's what this output function is kind of for, is that's what generates us our final random number output. But like I said, this is just the overall outline of what a lot of these algorithms look like. I wanted to provide information on a great algorithm I think y'all should look at. It's very fascinating. It's called the MT algorithm. It's something Twister. I can't remember for the life of me right now what the first name is, but just look up MT PRNG algorithm, and it's really cool because it's used a lot within C++ and Python libraries for random number generation. And I wanted to include it, but I also couldn't find very many credible sources that were giving good documentation on how it worked and what the code looked like. So I didn't want to give y'all any false or misleading information, so I just went ahead and just decided I would tell you all about it, but I couldn't bring any good factual information just because I couldn't find any credible resources at the moment to kind of give y'all good information on that. But it's definitely a fun one to look up. Definitely go look at those. But definitely, as you look more at the algorithms, you'll see a lot of these look like this kind of outline. And it's overall a pretty simple outline. You can make it as complex or as simple as you want. You could very easily go ahead and make your own algorithm if you wanted to, your own pseudo random number generator to do whatever you kind of need your random numbers to do with. And it's just pretty cool. But like I was saying earlier, the seed is pretty important. That's why we were talking about before using the mouse movement or other true random number generators for the seed of your pseudo random number generator. Because if the attacker or someone trying to attack you can ultimately figure out how you're computing your seed or where you get your seed from, they can compute the random numbers you're generating. Because like I said, if you use the same seed for the same algorithm, you're going to get the same result. Because an algorithm is ultimately just a function. It'll take the same input and it'll give you the same output. Nothing is going to change there. And so if you're going to be using the same seed, or you're going to have a pattern in how you get your seed, then if the attacker figures out that pattern, they'll be able to calculate the random numbers you're generating and figure out your keys. And so that's not good. So that's why I suggest using your true random number generations to basically calculate your seeds for your pseudo random number generations, because then there is no discernible pattern. There's no way the attacker can really calculate what your seed is. They can still guess it and they might get it. I'm not going to say that it's impenetrable because there's no such thing as that, but it does give you a good advantage over the attacker. And so that's kind of why I was talking about it during the mouse movement and the atmospheric noise, is that we can use those numbers we're generating that don't have discernible patterns and put that into our algorithms. So that's just a cool detail that I wanted to give to y'all. And we'll be talking more about, the differences between true and pseudo random number generation, kind of their outlooks and their aspects and how they kind of work with each other. Hey, so this is the kind of the last slide of this presentation. We're looking at the applications of random generation. We're kind of just tying up what we've been talking about for the last 20 or so minutes, kind of just putting it all together. So yeah, one thing from the last slide I also do want to mention that I kind of forgot to talk about, that I wanted to tell you all about, is there are actually some languages like C++ and Python. They have some methods that like built-in functions that generate random numbers, but the seeds they use automatically come from true random number generations. So some of them will actually call on what is the dev/u random function, and that basically calls upon the kernel's entropy pool to get random bits. And what the entropy pool basically is it's this storage of random bits that your kernel keeps, and it actually fills it using true random number generation. So we kind of see that with, it fills it with such as mouse movements and keyboard clicking, the timing between keyboard clicks. And we already talked about the mouse movements, as well as IDE timing. So it uses kind of those things to fill the entropy pool with random bits. And I said dev random, dev urandom and dev random are two different functions that can be called. It kind of just depends on whichever one is more proficient for whatever you need. The only difference is that dev urandom, what it'll do is when it calls it, it'll basically always pull from that entropy pool whether or not the bits are suitable or good random bits. The dev/random will only do it if the bits are suitable random bits. So basically, if the entropy pool kind of ran out of good random bits to use, then it'll basically not let you call any more random bits from it if you use the dev/random. However, the dev/urandom really doesn't care. It's just basically saying, I don't care what kind of bits you got left. I don't care how random it really is. I'll take it regardless. Anyways, I just want to tell you about that because it's just a cool mention of, languages already using true random generations for their pseudo-random number seeds, because it really is a really good thing to add into your pseudo-random generations to kind of make it a bit more secure, and they kind of pair well together in that sense. So I just want to tell you about that real quick before we hop into this final kind of wrapping up everything. And so, yeah, looking at the applications of random generation, we're kind of going to be comparing true random and pseudo random and kind of their applications and what their pros and cons and what they're good at ultimately, and how we can best use them in the future. And so, yeah, looking at true random, we see that it's really not efficient for generating large amounts of random values because you can't always know when there's going to be a really great storms coming through. If you're picking up on atmospheric noises and weather storms, you can't always know when there's going to be a lot of noises or voltages, coming in to, use as random numbers. And the same thing goes is you're not always going to be moving your mouse. You're not always going to be clicking your keyboard. So you're not always going to be generating random numbers. That's just a natural part of it. You're not always going to be doing that. And so it's really not efficient for large amounts of random numbers. If that's what you're looking for, you won't be able to get a huge amount. But on the flip side, it's still very secure. I mean, that's what we've been talking about. It's based on data that can't really be predicted or computed, so that's what makes it even more viable as a secure random number generation, is that you can't really predict it, you can't compute it. It's a lot harder for an attacker to get their hands on those kinds of numbers because the best they can do is just guess at what it is. And as long as we have them guessing, it buys us a lot of time. Now, on the flip side, we are looking at pseudo-random, and while true random is not efficient, pseudo-random algorithms are extremely efficient at generating large swaths of random integers or random values. It's great at that. That's what it's for. Algorithms will always be able to produce you how many integers you need. However you need it, you just keep running the algorithm. It doesn't have to stop. It can keep going as long as it needs to. That's what the algorithms are for, So it's very great at, if you need large amounts of random values, it's great at that. Now the downside, like we've been talking about, it's very insecure because it's an algorithm. Like I've said it many times, if you use the same seed on the same algorithm, you're going to get the same output regardless, So if you can put in the same seed and get the same output, the attacker can figure out that seed and get the same output, And so it's just a natural part of, this life is it's going to be insecure. If it can be copied, it can be replicated. Whereas true random values, it can't necessarily be replicated. You can't get the same storm to come through twice to get the same random values, but you can guess the same seed to get the same output value for pseudo-random integers. So we kind of see that's kind of where they kind of mirror each other. But yeah, looking at true random, it's great for using as seeds for the pseudo-random number generation. We kind of talked about that. They kind of pair well together in that you calculate the true random value and you use that as the seed for your pseudo-random. We already see, like I talked about, some languages are already doing that. They already have that in some of their methods. It's just great for just any cryptographic purpose. And ultimately, like what I'd say is just know what you need, what kind of numbers you need. When you're building your cryptographic system, you know what kind of keys you're going to need, what you're going to be looking at. If you're going to be needing a lot of keys and security isn't as important, then don't do true random. I would say do pseudo random, but pair it with true random seeds. But if you really don't need as many keys, definitely just stick with true random. Just calculate your true random values and use that as your keys. On the flip side, though, like I said, if you know you need a lot of keys or you need a lot of data or inputs, definitely go with pseudo random if security isn't your main priority. If the amount of data is greater than the quality of the data, definitely go with pseudo random. That'll get you all the data you need whenever you need it, and it's very predictable. And so that's what we see is it's great for modeling and statistical computing and just running simulations for different things. It's ultimately great for that. And so that's kind of where I'd leave us off is ultimately when you know what you need of what kind of data you need or what kind of values you're going to be generating, then you'll know what to look for, whether you'll need true random or pseudo random values. And yeah, that's kind of where I leave us off. And I just want to thank y'all for listening to this 30-minute presentation, kind of just listening and paying attention and just learning. And so thank you very much, and I hope you all have a great night.